Okay, so we will continue with our discussion of chelating exchangers, and we will look at the case where, which is very often the case, that you don't have just one ligand in the solution. Pretty much most of our contaminants, barring maybe couple, do have some ligand properties. So we have in the aqueous phase a situation where this, let's say we are trying to remove one heavy metal copper, but in solution there is not one ligand, there could be multiple ligands in solution. So we have a situation where in the aqueous phase you have these ligands. So what you have to then do is, of course, look at, you have to find, as I said, Smith and Martel is the most authoritative reference book where it's 4 volumes you get these constants, stability constants. And so you have to find out these stability constants, or get these stability constants, look at what is the concentration of each ligand in the aqueous phase, and what is the pH, and then you can come up. I mean, you know that this heavy metal that you're trying to remove, how it binds with these others. Okay? So, in a way, what I'm trying to say is that it could be an obstacle, because if you have competition among the ligands, then the one that you have chosen may not be able to remove as much copper as you had earlier thought when you didn't know that these other ligands were there. So I'll just show you one set of curves. We are trying to remove copper, okay? And so we load our resin and we pass the solution, and whenever it breaks through, that's where it is exhausted. So if I have in the aqueous phase perchlorate is a very poor ligand, and we can go into the chemistry as to why, but this is perhaps the closest you can get to an anion without any ligand property. Perchlorate and nitrate, these are the two most common. Okay, so if there is no ligand in the aqueous phase, you get this breakthrough. Now, if we put in sodium chloride is not a strong ligand, but it is still a ligand nevertheless. So it will offer competition. And what you do see is that, yes, if you put in chloride, half moles per liter, then the breakthrough is much earlier. And we see that in this as well. So the point is that if there is competition among the ligands, then our central heavy metal removal may be happening. Now, the next thing I would like to touch upon is, how do you make this contact? And we have talked of column, and column is the most common way in which contact is established, contact between the exchanger and the solution. But there are certain issues with a regular column. So people have been looking at how to make this contact more favorable. And the best technology that's available is called as the RICO flow. That's the trade name. It's a patented process. It's a short bed process. Okay, let's see what it does. So here we have. Now keep in mind that when we are looking at a column, then the head loss across the column is directly or is inversely proportional to the square of the diameter. So the smaller the diameter, we know from classical fluid mechanics, the greater the head loss. So what we do in this Day-4 flow, it's a very short bed, okay? What do we get? The advantage by the short bed is that we have a much smaller L. What is the disadvantage? We have a much smaller D sub P. So if you don't do anything, if you just have a much smaller D sub T particle diameter, and if you keep the L the same, then the head loss would become unbearable. So we take very fine resin particles, but in order that the column will not be subject to very severe head loss, we reduce the length. And so it's much finer particle size, typically 100 to 200 mesh, and your flow time is very short. You can see 2 minutes to 1 hour. When we run typical commercial columns, we run it for days together before it is exhausted. But here, we are running it only for a few minutes. Okay, but it is not a big inconvenience because the process is set up in such a way. That we have multiple these small columns. Okay, and it is all mechanized and automated so that after 2 minutes or so, let's say we are running it for 10 minutes. After 10 minutes, this will turn 1 notch and your flow would be directed to an empty column or a virgin column as we call it. And that, the 10-minute column which is exhausted now will be regenerated. So it is all done without much need for personnel interfering or trying to control the system. So what we get out of this kind of a reactor is much better kinetics, which gives us much better performance because, as you know, kinetics is, I mean, until now we've been talking of equilibrium, but kinetics also plays a role. If the kinetics is very poor, then the column efficiency is compromised. But here, because we are running we are running with very small particle diameter, kinetics is much better. Because as you saw yesterday, the kinetics is pretty much intraparticle diffusion kinetics, is pretty much dependent on the diameter of the particle. So if I can reduce the particle size, let's say by 3 times, my kinetics is 9 times faster. So this is something we do very often. We use these kinds of reactors. Then the next thing that I would like to touch upon is what happens if we have situations where the aqueous phase is very unfavorable. And the most common example that we get is with metallurgical operations or hydrometallurgical operations. What happens there is that typically the solution from which you're trying to extract the heavy metal is very acidic. And if I put a strong acid cation, let's say I'm trying to remove copper from a very acidic solution, from an acid mine drainage solution, let's say, then if I put in a strong cation exchanger, strong acid cation exchanger, it will not work because, as we saw, the swelling and shrinkage would be so much, and this resin would be compromised because a strong acid would kind of destroy some of these sites or some of the backbone of the polymer also. So if you have a situation like this, then a regular chelating functionality may not work. You have to look at some novel chelating functionality. Okay? So, for example, strong acid will not work. But even a regular weak acid like an immunodiacetate or carboxylate will not work. So that's when we go to systems where, for example, the one that we discussed the other day, with only nitrogen donor atoms. So if you have no oxygen and if you have no phosphorus, then this kind of resin would be able to perform at extremely low pH without, without where is it? Extremely low pH without any loss of efficiency. Okay? And the one that comes to mind, or the two that come to mind, are these three compounds. This is called Dow 3N or Dow XFS 4195, three nitrogen donor atoms, and the other one is Dow 2N, which is two donor atoms, 43084. Okay, so the point that I'm trying to make is that we have to understand our situation before we decide on, before we start the separation process. We have to look at the aqueous phase, what all are there, and in terms of heavy metal removal, what all ligands are possible. We have to model their ligand. We have to use a model where we are inputting these metal ligand stability constants, and then we have to look at what would be the best resin. And sometimes, because of, let's say in this case, our choice is very restricted. If I have, as we do in some hydrometallurgical cases, pH of 2, pH of 1, then we don't have much choice except these two resins, commercially speaking. Okay, so now, all this time we have been talking of removing we have not reached the recovery phase yet. Just we are talking of the removal of the heavy metal, but our heavy metal was in a pure solution. It would be very acidic, it would have multiple ligands, but it was all pure solution. Now, that is the case with many industrial wastewaters, and sometimes if the industrial wastewater does have some suspended solids, we can remove them very easily and make a pure solution, which we then feed into a column. But if we have a situation where we are looking at soil decontamination, for example, then this process needs to be revisited or revised, because if I'm looking at soil and if I have a soil slurry with very high suspended solids, then of course this process will not work. So what do we do? So we look at a chelating exchanger or an ion exchanger, but the morphology now needs to be changed. So I would like to discuss a little bit how one can get exchangers with some different kinds of morphology. Okay. So bear with me for a moment. So we can look at exchangers, but now they are not just as resins, but they are typically either as a membrane, and and ion exchange membranes are very common. So in membrane, there is not much of a novelty. I mean, people who work in membranes with membranes, they come up with new membranes with new functional groups and all that. But the morphology is pretty much well established. I would like to spend some time on two kind of novel morphologies, where in one, it is not a membrane, it's a sheet. And the difference is that in a membrane, the particles, if you look at them as these chelating exchangers, they are much, much more densely packed. Membrane, the water is passing kind of perpendicular when you put a barrier. So when you pass the water, and in this case, it need not be a case like that. Here, what we are doing is it's called a sheet, composite sheet. So you have these particles, and in membrane, typically you want to make all the particles of the same size. So you, when you get your original particles, you sieve them so that there is uniformity. The uniformity coefficient is very high. Whereas here, you don't want that. You want a particle size distribution so that at the end of it all, when you have all these particles of a different, a much lower uniformity coefficient, if you now entrap them in a Teflon sheet, in a Teflon, you get a sheet which is typically maybe 0.3, 0.4, 0.5 millimeter in thickness, and it has these particles which do the job for you. And our job as synthesis chemists or synthesis engineers is to make sure that these sites are available, because there is always the danger if you put too much Teflon, the Teflon would cover these particles. Okay. So that is one composite sheet, and the other is a fiber. And with fibers, it's a derivative of textile technology. In textiles, they deal with fibers all the time. But in our case, these fibers, the only unique thing is that these are all submicron fibers. All of them have a diameter, the range of, I would say, maximum of maybe 800 nanometers. So somewhere between 100 to 800 nanometer diameter. Okay. So the question is, how do you make it, and then what good is it? What benefits would it be? So let's look at that. Okay, so one area which is completely a different area now is the biomedical application. Okay, so we have a big area of biomedical research where we are looking at tissue engineering. So the idea is, as you can see, you take out some cells from the human body where the organ is affected, and you kind of grow cells outside, and then you put them in some kind of a matrix so that these cells will not be detached. Put it back in the system, back in the. So the question is these scaffolds. Okay, how can we make these scaffolds where when I put these cells, then they stick? Because if they don't stick, if they disintegrate, then you have a problem. So what one can do is you make these scaffolds using fibers, and the fibers that we get, they can be a solid fiber, or if you can make hollow fibers, so much the better. Okay? So this is an example of a hollow fiber, and these are the solid fibers. these fibers, they need to be, as I said, sub-micron, preferably less than 300 nanometers. That because you see what's happening is that the cells that you are taking out from the human body, they, in order to grow them on the scaffold, they should not reject the scaffold. Why will they reject the scaffold? I mean, this is a new environment for these cells. So if you have very thick fibers, then attachment onto those thick fibers is very difficult for the cell. And even if somehow you can get it attached, it's not going to grow. So in order for these cells to grow very fast, you need a very fine network. But that is a completely different area which is unrelated to our course. Our course relates to resource recovery. So when we are looking at resource recovery, then the fibers that we have in mind are ion exchange fibers. And so the question is, how do we make an ion exchange fiber? So just to kind of give you a little bit of an overall view, when we deal with a resin, what is a resin? It's a very strong electrolyte solution, as we have discussed many times. So in the resin, we have this bead, and inside the bead, in this very strong electrolyte solution, we have these functional groups. So for a counter ion to, let's say, if a counter ion has to, let's say this is sodium, and I want it to be now replaced with copper. So copper is here. Now for this ion exchange to occur, keep in mind what has to happen. The copper has to diffuse to all this length, come near this sodium, and then based on law of mass action, sodium will come out and copper will go in. And the other thing is this sodium has to come out before the next copper can go in, right? So the point being that with the resins that we have, this kinetics becomes an important challenge. If I can take the backbone, and if I then am able to put functional groups kind of jutting out of the backbone, then these functional groups, they are much more easily available to the counter ion. So that's the idea, that the benefit of a fiber is that it will give us much stronger kinetics because the diffusional path now has been reduced substantially. That's the general hypothesis. Okay, so it has higher surface area because once you put these functional groups inside the bead, many of these have steric hindrances, etc., etc. So even if I, let's say, very simplistically speaking, there are 10 sites, 10 functional group sites in this and 10 in here, even then this will have a higher surface area because they are all available. That's the idea. Faster kinetics, I talked about it. Now, this fiber we can very easily use in a situation where we have high suspended solids because the fiber can be immersed in it, the fiber can sit in it. So if we're looking at an in situ, we talked of in situ treatment yesterday. If it's an in situ treatment, which is a slow process, we can conceive of situations where we put this fiber in the soil and let it sit for, let's say, a week. And after a week, we come back, take the fiber out, and hopefully within those 7 days, the ion exchange would be complete. So, yes.
Soil is in liquid or solid phase?
Solid.
So the ion exchange will take the solid phase.
But I mean, when we say solid, it is not a dry solid. It is very saturated, and it is in the pores that all these contaminants are. So it's a sediment, for example. This is a typical application is a sediment.
It is like a fluid. Right?
No, not fluid. Let's say you go to a river bank and the sediment is now contaminated. I mean, we have all this many situations where I mean, the best example would be GE, General Electric. What they used to do was they used to make these transformers, and in the use of these transformers, they would use a lot of PCBs, polychlorinated biphenyls. And in those days, 1950s, 1960s, they would dump whatever PCB they did not use into the river, the Housatonic River. And so slowly these PCBs, they reached the sediment, they went into the sediment, and now these sediments are contaminated. But keep in mind, the sediment is in equilibrium with the overlying water. So there is no oozing out of this all the time. Those are the kinds of situations. So what I'm trying to say is, if I can draw it, is that I'm looking at it, I mean, a longitudinal profile. Let's say this is your water surface, and you have these sediments. Now, of course, this is under saturation. All the pores here are saturated with the water, and if they are saturated with the water, they also have the same concentration of the metal that we are trying to remove.
So where will we place this level?
Where to place it? Let's look at the idea first. What we typically do is we loosen up. Let's say this is, of course, the water layer, and say this is the soil, this is the sediment layer. So we loosen up this top few inches, and then we place this. But keep in mind, we have not done experiments like that. Experiments that I will show you are all done in the lab.
Because, sir, when
But-
ions will migrate, it needs some fluid part.
The fluid is there in the sediment. Yes, the sediment is, I mean, the pores of the sediment are full of the fluid. So to answer the earlier question, before you go to the site to do pilot scale test, you have to be absolutely convinced that it works in the lab. So right now I'm still in the lab. So what we do is we take a polymer and then to some very well-known chemistry, we convert it into the functional group that we are looking at. So I will just show work with polycaprolactone and polyacrylonitrile. And the process of polymerization is pretty well established. I mean, polymer scientists, they do it all the time. So we understand the process. Now, in our case, what we do is we take this polymer and we make a fiber out of it, and I'll come to how we make the fiber. And then on this functionalized surface, I mean, now what happens is that the fiber is kind of jutting out of this surface. And because this is very easily accessible, we can now put a biomolecule or whatever heavy metal we are removing. So the process is not at this surface, but a few nanometers above. And that's all I would like you to keep in mind. So the process that we use is called electrospinning. Electrospinning is pretty well, you can say it's a mature technology. What do we do? What we do is we take this polymer and we dissolve it in a solvent. And this polymer solvent mixture, if we now put it under a very strong electric gradient, we have a very strong electric gradient. And now if we just, let's say the lab scale, if we just this syringe, what will happen is that the droplet of this polymer solvent mixture will just try to come out. And now, because this droplet is under a very strong electric gradient, it would tend to go to the collector. But because this mixture has a very high percent of solvent, the idea is by the time it reaches the collector, the solvent would have come. And what you would get then is, because of this very high surface tension, you would get these stretched polymer, which will, of course, when we say stretched, it is a fiber. So that's the idea. And in a lab scale, it looks something like this. This is the electricity unit. These are the syringes. And of course, because we are dealing with sometimes nasty solvents, we have to have a very controlled atmosphere. I mean, we can't allow the solvent to come out. It has to be under negative pressure in a few. So this is how it looks. It's called a Taylor cone. That's the technical word that they use. As you push this solution, it tries to come out. And of course, we know from high school physics that the shape it will take is that of a sphere. But now keep in mind that we have this very high electric gradient. So the sphere is now stretched. And so what you see at the tip is this stretched mixture. As it leaves, it gets more and more stretched. And as I said, the trick is to design the system such that by the time it leaves here to the time it gets here, the solvent evaporates. So you get this pure fiber. Pure meaning just the polymer. So this process, as I said, electrospinning is not new process, but it does not have many applications. Our thought was to come up with electrospun polymeric ion exchange fibers so that we can extend the range of ion exchange. But as you can see in the lab, it's a very slow process. In the lab, when you have a unit like this, typically, if you run this unit for a few hours, let's say 3 to 4 hours is the most common. Of course, it depends on the polymer solvent mixture and all that. Typically, polyacrylonitrile, when you try to spin, electrospin, I mean, in 3-4 hours, we would get only maybe 5 grams, 10 grams of this material. Very slow process. So, of course, that process has to be expedited. How do you expedite? There are all these, I wouldn't say commercial scale, but much bigger than this. This is still lab scale, but now this is called a nano spider. That's the technical name. It's manufactured by this company, El Marco. It's a Czech company. But now you can take, it's called a tray. On this tray, you can't really see very well. On this tray, you put this polymer solvent mixture, and now you have all these controls. So you need to know there are 2 kinds of trays. This is what we call the long tray, and then there is a droplet tray. So you take a droplet, and then you see what is the best electric gradient. Typical electric gradients would be 15,000 volts, 20,000 volts, 30,000 volts. So, because this distance is so small from the tip to the collector, that you need this very high electric gradient because otherwise the process, you will not get the pipe. So, very high electric gradient, that's all I'm saying. So, you need to put it in a very safe environment. So you take this droplet and you then see what is the best distance between the collector. So once again, you can't really see very well, but this collector surface can be manipulated both ways, vertically and horizontally. So by vertical manipulation, you then know what is the best distance. And by horizontal, what happens is that there is a conveyor belt fabric on a conveyor belt. So as the fiber fibers are being generated, this conveyor belt is moving, so you get a mat. And the regular process, what we call the vanilla process will not give you aligned fibers. They will just give you a random collection of fibers. Just imagine, fibers are being made, and as they get to the collector, when they hit the collector, they just stick it. Okay. Now, there cannot be much alignment because these fibers their generation is very random. So there are two things you can do, which we have done. One is that you rock this conveyor. So it goes like this, comes back, goes like this, comes back. What happens then? What happens then is that all the fibers that you are generating, they are now collected over a small area. And so you get a thicker mat. So the resulting is a mat. And that mat thickness, you can now, you have some control. But aligning fibers is a whole different ball game. And I will not get too much into that. There are techniques by which you can get aligned fibers, and a lot of people are working in this area. But all I can say is that for our purposes, a mat that I will show you a picture of, that kind of mat was good enough for what we did. So we didn't really need very aligned fibers, because even if the fibers are random, we are taking this mat and then we are functionalizing. So as long as the mat is thin enough for this functionalization solution to pass through without much interference or without much obstruction, we are okay. What I'm trying to say is that suppose you have this mat. You take this mat and you then put it in your functionalization solution. And kind of keep it hanging on suspension bed. And now this functionalizing solution, whether it is heated or whatnot, the functional groups would then move from the solution into your mat. And depending on how you do the functionalization, that means where these sites are, it'll have some capacity. So, in this case, you don't really need an aligned fiber. But if you are doing, let's say, nanofibers for applications in wafer technology, there you need aligned fibers, which we don't need, so we will not talk about it. Okay, so this is the fiber mat that we spun, and this is of course solid fiber. They do have these benefits, very tunable, because we have full control of the starting polymer. We have full control over the solvent, and we have full control over the distribution. Typically, the data that I will show you is about, let's say, 5% polymer, 95% solvent, 6% polymer, 94% solvent. So you can change this mixture. Of course, keep in mind, let me go back a little. Keep in mind that when you make your polymer solvent mixture, the viscosity is very, very critical, right? Because if it is very viscous, it will not even want to come out of your syringe, and you would not be able to form a fiber. So, and if it is if the viscosity is very, very low, what will happen is that the time that this material gets to stretch will be so short that you will not be able to get these fibers. So there is what is called as the Goldilocks spot, which will vary from polymer to polymer. So the point that I'm trying to make is that you have to do a lot of homework before you go in to try to spin something like this. You have to look at the viscosities. You have to see which viscosity range you have to be in. You have to see what is the polymer evaporation rate, because not all polymers, I mean, it all depends on their Henry's constant, of course, but keep in mind that you have to evaporate all the polymer, all the solvent before the fiber reaches the surface. Otherwise, once you get this coating of the solvent, then the fiber, after this process, then you don't have really time to manipulate it anymore. So, lot of homework, and there is no guarantee that if you do a lot of homework, you will be successful. I mean, we spent weeks and months trying to get fibers, even though literature review suggested that other people got results, and all the physics, all the fluid mechanics part seemed to be alright, and yet so it's a, you can say, trial and error technology. Because what happens is that in this unit you can blow air, okay? And you do need to blow air because you're trying to the solvent, the volatile solvent, you're trying to drive it out. So if you push in more air, the solvent will evaporate faster. That's no. But besides air, you can also put in nitrogen, for example. You can put in a design cocktail of air so that your volatilization rate is what you want. And so what I'm trying to say is many variables. Yeah, it's viscosity you can measure very easily. The viscometer is a very standard, it's a very cheap instrument. Pardon me? Rheometer also. Rheometer also can do it, yeah. So now the question is, these are all solid fibers. I mean, can we make hollow fibers? That is another big leap. We have not been able to get hollow fibers. And we have not been able to get it because the technology for making hollow fibers, as I understand it, is available with only 2 vendors. And we did contact one of them in Switzerland, but what they have now is not good unit for TAN that we were, I mean, polyacrylamide nitride that we were interested in. So we have not been able to make hollow fibers. If and when we are able to do so, our applications potential will increase manifold. But all the data that I will present is solid fiber. So, as I said, you have to look at the polymer concentration. You have to look at the voltage. You have to look at the collector distance, and after you get the polymer, then you have to now functionalize it. So the functionalizing techniques, I mean, what kind of binding force do you put in? And there is a whole range of binding. You can have a coating. That means you get the fiber and you dip the fiber in your solution, and the solution, it will generate functional groups on the surface. So that is the coating part. You can do what is known as co-electrospinning. That means you take the polymer solvent and also the functionalization agent, and then you spin. Of course, it's very much more difficult than I'm saying it. But the idea is that as this fiber is being formed, functional groups are also formed. Okay? So that's a very neat technique, but not at all easy to get good results. And then you can do something which we have not done, but others have done. You can go in for much stronger binding. As you know, physical coating is a very weak coat. There is always a chance that this functional group would detach from the polymer. But if you do a plasma treatment, for example, then it would attach much more firmly. But we have not done these two. So I cannot speak of what would be the challenges with plasma treatment. So what we do is basically wet chemical techniques, and because we are looking at this scaffold for tissue regeneration, so it's kind of a parallel research. The student who has now graduated, the student was working on electrospun fibers. For a few months, he would take polycaprolactone, spin it, work on the tissue regeneration research, which was advised by a colleague of mine in the mechanical engineering department. Then she would take the polymer solvent, spin nanofiber, and functionalize it and work on ion exchange part with me. So when you are doing it for tissue regeneration, then your functional groups, of course, are different than in our case. So challenges are that, of course, physics or mathematics will tell you that yes, if you put this in your functionalization reaction, you will get, based on stereochemistry, you will get so many sites. You can do those calculations very easily. You can do that calculation that if I have a solid fiber which is 500 nanometer in diameter and let's say 250 millimeter in length, if I now put this in my functionalization solution, what would be the ion exchange capacity? You can do that calculation very easily. But the problem is that the answer that you get is nowhere close to what you are getting in the lab. Why is that? Well, that calculation is based on uniform distribution of functional groups, uniform accessibility, so many things. And our situation is much more complex than that. Then comes the question of kinetics. Kinetics of functionalization, you look at what others have done before you, and based on that, you try to manipulate your solution. So whether the solution has to be heated, whether there has to be stirring, all those things, but still, it's not an exact science. Again, a lot of trial and error. And then the most challenging, perhaps, in our research at least, was the density or distribution. One day you spin and you do a functional group functionalization, you get, let's say, I'm making up numbers, let's say you can get 2 milliequivalents per gram. Another day, you do exactly the same process, you get 3 milliequivalents per gram. You're very, very happy. Third day, it becomes 1 milliequivalent per gram. So it's a very difficult to control. And then the most important question is the depth of penetration, because keep in mind, when we look at the kinetics, which I'll get into in a moment, or maybe after. Let's see. The point that I was trying to make is that how deep does the functional group go? So you have this solid polymer, solid fiber, okay, and you are then hitting it with the functionalization reagent, and you are creating these sites. Now, it depends on how much this can penetrate. How many nanometers from the surface? So that will tell you, that will give you your equilibrium capacity. That will be a very important metric in the kinetics, because when you are doing kinetics, your flux curve, this is how it would look like. Right? So the point being that this thickness will play an important role. You have to control it, you have to know it, and that is the parameter that you will then put in the model. So I'm saying things, it might seem very simple, but when you go to the lab, you will see that there are many variables that can play a trick on us, and they do play a trick on us. So one has to be patient, and that is something which has nothing to do with electrospinning. It is common to all research. Patience is the most prized attribute that you need. If you are not patient, you will never succeed in research. Okay, lot of advising. Let's look at. It is you try to make it porous. How do you make it porous? Well, you the possible two ways. I mean, the one that we do is sonicated. So you take this fiber and you put it in a sonication chamber, and the idea being that the sound energy waves would bombard it and would loosen it up. But to put it very bluntly, we didn't really get much benefit from that. The other literature, the other path that literature suggests is microwave treatment. We didn't try it, but I know one of my friends at the university in Ohio, same polymer, he tried microwave treatment, he didn't get much benefit either. So the literature has all these techniques, and they may have worked for the polymer that that particular research group is working with. We were not able to get much benefit. But you are very correct that one has to loosen this up, because when you get this polymer, it is so dense that trying to put a functional group on it is very difficult, if not impossible.
If you make it a solution is concentrated and put it for longer time,
which solution is concentrated?
Means a functional group solution. If you make it concentrated and you put it the fiber for longer period, I think
no. You don't get any benefit of time, because this is all, you can say, equilibrium chemistry related. So if you have, let's say, as in our case, we have sodium hydroxide, 2 normal, let's say, 2 normal sodium hydroxide at a temperature of, let's say, 57 C. If you make it 4 normal at 90 C, it's not going to give you much better results. It's not like that. Well, I mean, we are trying to functionalize basically the data that I would show is polyacrylonitrile, and others have worked with polyacrylonitrile, and they seem to suggest they got some results. We didn't. So, what exactly was the difference between their setup and ours? I don't know. Because when you read a paper, the paper, of course, it is supposed to give you all the details, but sometimes.
So is there any advantage of using this polymer over other polymers?
Well, the advantage with PAN is its functionalization, and I will show you that. I mean, when you take PAN, you can very easily convert it into a weak acid chelating exchange. You just basically take this fiber and put it in sodium hydroxide. Again, as I said, there are 3 variables: time, temperature, and the concentration.
Actually, mechanical state is more compared to polyacryl. This mechanical state.
Compared to which one?
Polyacryl. What is the material?
almost impossible to electrospin. Polystyrene you can spin, which we did spin. The challenge with polystyrene was that so hydrophobic that putting functional groups became the limiting issue. So calculation would suggest that you may get, let's say, 5 milliequivalents per gram. We were able to get only 1 milliequivalent. So we did try polystyrene as well, but because our success was so limited, I will not show you any data. Work is still good. And with, I can just share one small piece of information. With polystyrene, when you have to put in a sulfonic acid group, what you do is there are basically two techniques. One is you take sulfuric acid with silver, and silver is a very good initiator, and then you kind of heat the system, and the literature is full of cases where they were able to generate this sulfonic acid functional group. In our case, as I said, we were able to get it, but not to the extent that we would like it. The other way is you use chlorosulfonic acid, and chlorosulfonic acid is very, very aggressive, and it needs a lot of safety protocols and so forth and so on. When we would do that, the polymer would disintegrate. And of course, if the polymer disintegrates, if the fiber disintegrates, then there's nothing really left for you to work with. All right. Pendraji, how long should we go on in this session? 10 minutes more? Okay. So I would like to show you the work with tissue regeneration. And the idea is that, well, you want cells to attach, so you want the cellular response to be better, and this is exactly what we see. That initially you have very, very few cells, but then as time progresses, you get a very dense colony of cells, which is what we want. But the question is there, as you read here, is there a direct correlation between the functional group density and cellular response? In other words, if I can put 2 milliequivalents per gram of functional group, I get a certain cellular response. If I increase it to 4, would the cellular response be double? And the short answer is not necessary, because, of course, the functional group does have a role, but it's not a linear correlation. And the other question is, as you read here, does it exert its influence at early cell attachment stage, or is it that there is a behind factor? So, with polycaprolactone, this is now the functionalization part. Hydrolyze it, you then aminate it, and then the idea is you can attach some biomolecule. And the biomolecule could be a drug. And we looked at a couple of drugs, but most of the work was with proteins. So the functionalization, again, it's not anything that we did. We just went to literature, and literature is very vast and standardized to some extent. Now, if you're looking at a biodegradable polyester, then what kinds of degeneration do they go in? Well, they can have what is known as accelerated degradation or slow over time. And it, of course, depends on the hydrophobicity, as you can imagine, the configuration, and the crystallinity. So I'll just show you the results. So you take polycaprolactone, and as I said, you have this ability to vary concentration. take it in, I mean, the solvent in our case was acetone. And as you know, when you deal with such polymer, its molecular weight also is very important. We were kind of surprised. Um, we started with PCL from one vendor, and we were pretty successful. And then we ran out of that batch, and we bought another batch from the same supplier. And Manisha, the student, she started working on the second batch. She would not get any fiber. So she was very frustrated. Then when we kind of brainstormed and started to think, then it hit us that maybe this was a different molecular weight. And indeed that was the case. Apparently, when you supply polycaprolactone, based on how they make it, they meaning the chemical supplier, this molecular weight would vary anywhere from 60,000 to 120,000. And so you have to know that. And in our case, 80,000 was fine, 100,000 was not. So these are some of the things which one has to keep in mind. Of course, the flow rate, the voltage, and the needle distance. So what you see is that when you have 10%, you get 240 nanometers average diameter. So of course, this is average diameter. What happens is you get a variety of diameters, and you take them to SEM, and then you zone in different paths, and then there is a software. It kind of takes all this data, averages it out. So 240 nanometers, pretty consistent fibers. But when you increase the PCL percentage, fiber diameter increases. And of course, now when you make these nanofibers, there is something called beading. Beading is a very bad thing. If you get these beads, that means your spinning is not. And so, even though you might say, "Oh, this is perfect because this is 240 nanometers," but this fiber is not very user friendly. Even though this is much higher in terms of the average diameter, because you don't get beads, this is a much better material. Then you do XPS. We were talking about XPS yesterday. So you look at how much you were able to aminate or whatever, and that you look at by the difference, which is very standard. And then I would like to show you some results as to, well, based on the average diameter, how much you were able to get based on this hydrolyzed PCL, 30 minutes, 3 hours, we are looking at cell density, 8 hours, 24 hours. So now let's look at, I think we should stop here, and then we will look at the ion exchange part when we come back. So when we come back, we will look at this ion exchange fiber. We will look at the composite sheet, and then we will do a tutorial kind of a problem solving. So it's a tall order in 1 hour doing all these 3 things, but we will do as much as we can. Okay, time for a break. Questions? All right. We will be back in what, 10 minutes, Upendraji? Please, 10 minutes. when we discussed for our tea break that when we talk of ion exchangers, then we have basically four big. They can, first two and then two more. First two would be what kind of an exchanger is it? What does it exchange, cation or anion? And within cations, it could be a strong acid or a weak acid, and within anion, strong base or a weak base. So, so we are looking at nanofibers, and as I said, there are some benefits. So the first nanofiber that we electrospun was polyacrylonitrile. Why? This question came up during the tea break. Why did we go with polyacrylonitrile? And the answer is very simple, that it has the mechanical stability and the thermal stability that you need, and it is resistant to some of the things that this eventual fiber may be subjected to, like heat and sunlight. So you need that resistance, and it is very common polymeric material, so it's available very easily. And the main reason, of course, as you can guess, is because of these nitride. So C triple bond N gives a lot of versatility, and this C triple bond N is what we exploit for our purpose. So one can look at amination. How do you aminate it? Well, very standard process, as you see on the screen. What did we do? We took AN, which is in this case much higher molecular weight, 150,000 grams per mole, and we took DMF. DMF is a very common solvent in electrospinning, dimethylformamide, and it was 10 to 90. That means 10% polymer and 90% solvent. 20,000 volts the potential difference, and needle to collect a distance of 9 inches. As you can see, the viscosity is much higher than with the earlier data that I showed. What are the amination conditions? The aminating agent that we used was diethylene triamine, 33%, 105.6 degrees C under reflux. Of course, you need the reflux because you are doing it for 18 hours. And as I was saying before, we discussed that when you look at aminated ion exchangers, the beads, their capacity typically is 2.5 millimolar per gram. Our capacity is much, much lower. So when you get the electrospun, ES means electrospun fan. You see this is 10 micron, so this would be less than a micron. And when you laminate it, you see that you get this, you see this very thick kind of band that deposits, and that makes the fiber diameter much higher. And whenever we, as I was saying before, whenever we deal with electrospun fibers, we get a distribution. So we look at different fibers and different, we average it out. So this, when we say diameter of 680, that's, keep in mind, that's based on some distribution. And this, what, as I was saying, is that when you aminate it, then your fiber diameter increases substantially. So from 680 to 18. And then with, as with any, excuse me for a moment. Okay, so as with any material, one has to then characterize it. So you do XPS, you do FTIR, and then all these, and you look at the shift in terms of XPS. You look at the shift in the band energy and binding energy. So let's go to another one, weak acid. And when we look at weak acid, this is what I was talking about. It is polyacrylonitrile, and as I was saying, we exploit this C triple bond. And what I meant by exploitation is that we can now put in a carboxylate. Okay, so if you put it in a high pH solution, then you can break this bond, right? And you can attach an oxygen here, and then the next step would be that this carbon attaches to another oxygen, and the ammonia is set free. So very standard synthesis chemistry. So in our case, this work that I'm showing is with 150,000 grams per mole. The earlier work was with 80,000 grams per mole. And as I said, 80,000 worked fine, 150,000 worked fine, 100,000 did not work fine. So it's a lot of these variables. Anyway, so our hydrolysis condition was one normal sodium hydroxide or potassium hydroxide at a temperature of 70 for 30 minutes. And we get average fiber diameter of about 700 nanometers. And once you will electrospin it, then you get this exchange capacity. And the exchange capacity that we were getting with potassium hydroxide is higher than with sodium hydroxide. And there's a reason to it. I don't have the time to get into the details, but if you look at our publication, it's spelled out there very clearly. Okay, so all right. So you look at XPS data, you look at what is the ratio. This is very standard. You look at FTIR. So this is how it looks like. 50 times, 500 times, 2500 times. Again, when you zoom in real hard, you see these crevices, which seem to indicate that your functionalization did kind of penetrate a few nanometers beyond the surface. So now, what is interesting about our research was that you get this fiber, functionalize it, you use it to do the ion exchange that you are planning to do. In this case, it was to remove copper. If this material becomes dry, it immediately powderizes. So there is some kind of a hydrogel formation that's going on. If you keep it wet, perfectly fine. So then, how about strong acid cation exchanges? This is what I was saying, that you can take polystyrene, and when you hit it with sulfuric acid under heat with silver sulfate as the catalyst, then you can get the sulfonic acid functionalization. This is 98% H2SO4 with Ag2SO4 as the catalyst. So the point that I'm trying to make is that when we electrospin, the solution conditions are very aggressive. So one has to be very, very careful. As you can imagine, working with 98% H2SO4 at 70 degrees Celsius with a lot of silver, this is not an ideal solution that you would want to work with in the lab. So again, you characterize, and so what we find then is that if we are looking at polystyrene, strong acid, an average diameter of about 550 nanometers, the capacity, maximum capacity, I wouldn't say this is the average of all, the maximum capacity is 2, the calcium to sodium separation factor is 8. If I take, again, a polystyrene, but now if I mix it with polyisoprene, if you look at the literature, a lot of people do that because that provides you with much more mechanical stability, physical stability. So when you do that, you get pretty much the same average diameter, a little reduced capacity, and a little reduced separation factor. Weak acid Taran and 700 nanometers, about 2.4 milliequivalents per gram, with the copper to sodium separation factor of about 50, which I think is pretty good. And weak base anion, as I said, half milliequivalents per liter. So we did not pursue further work with this because we are still trying to get it to, you can say, at least 1 milliequivalent per gram before we can really start to think of applications of it. So then the question is, well, I said in the beginning that this is faster kinetics, and that is true, but one has to verify it. So when you verify it, you have to make a mathematical model. So this is the model that we developed. And this is not, when I say we developed, I'm not at all suggesting that nobody else has done this. Many people have done this for their particular situation. But all I want to say is this is a moving boundary problem. So when you try to model it as a moving boundary, then you need to be very careful with this penetration. So this is the original equation, and we are looking at a fiber of a certain length. As you can imagine, the length doesn't really play a role. We are looking at the exchange taking place across the surface. So you start with this equation, then you apply the initial conditions, the boundary conditions, and all that. This is something so standard that there's nothing that I have to say in terms of you. So you do all this manipulation. I mean, if you read this publication, you will get all the details and further simplification. So one can do it. Now, more important for us are applications. So what is the first application? The first application that we looked into is water softening. As I was saying yesterday, water softening is an area where most of the ion exchanger, the strong acid cation exchanger is used. But if you take a course in drinking water treatment, for example, then we see that there are two ways to soften the water. One is this traditional one called the lime soda softening. And lime soda softening works fine, except that it produces a huge amount of sludge. And I know of a few drinking water treatment plants in the United States which are finding it very difficult to dispose this sludge. Now, you will say, what is it about this sludge that it is difficult to dispose of? It's just that the quantity and the cost part of it. There is nothing hazardous in the sludge. Lime soda sludge is basically calcium carbonate and magnesium hydroxide. It's not the point. The point is that it is so much water that even after you put it through a bell filter or whatnot, the water content still is so high that you are paying a lot of money to transport water, which makes no sense, right? So, ion exchange is a very mature technology for water softening. We need, I mean, there are so many commercial units on it, but when we do ion exchange, then we need a strong acid as a regenerant, and the disposal of this regenerant is a major challenge. So our idea was, can we take the advantage of fiber as opposed to resin? In resin, as I was saying in the pre-break session, that this counter ion has to travel this path and it has all this resistance before it can meet the exchanging counter ion and the exchange can take place. So the kinetics is such that you need a very strong regenerator. And in a fiber, because it's open, the sides are so much open, there is not much diffusional resistance that occurs. So the idea is very simple. Let us suppose we have weak acid cation exchange fiber. Whenever we put an over bar, it is an exchanger. So in this case, the exchanger is a fiber. Now, in the water, if it is typically, as you know, when we deal with hard waters, most of the time it comes with alkalinity. Not to say all the time, but in this is an example where there is enough alkalinity. Not that the alkalinity plays a very important role, but in this case, if there is a lot of alkalinity, it will be calcium carbonate. So this water passes through this material, this fiber, and there is exchange between H plus and Ca2 plus. Why? Because, as you can see, you are forming carbonic acid, and the carbonic acid keeps the pH depressed. And and the same with magnesium. And the question is, when it is time to regenerate, can we regenerate using H plus not from a mineral acid, but from carbon dioxide? And of course, it depends on what is the particle pressure of carbon dioxide. So when we look at flue gas, it's typically less than 20% carbon dioxide. And why is it less than 20%? Because oxygen is only 21% to begin with, right? So anyway, so the overall reaction, regeneration reaction, I mean, if you have the fiber which is loaded with calcium, is that you pass carbon dioxide through your regenerate solution, and that would depress the pH so much that now H plus would be favored and calcium would come out, and you would then be able to complete the process. That's the idea.
And it's just doing the pH only.
Yes, absolutely. So this is how it looks like in the lab. We have a column which has been now packed with these fibers, and you run the column to soften the water. So you have the calcium, magnesium, sodium, and all that, and it goes through the column, and the hardening ions are removed, and you get the softened water. Now, when this is exhausted, now this is pressurized snow melt. We are using snow melt because snow melt does not have any alkalinity. Okay, so you then bring in carbon dioxide, pressure, of course, and then pump it. So let's see the exhaustion part. So you have this column, and we have about a 5-minute EBCD, and this is calcium of 50 milligrams per liter, calcium of 25 milligrams per liter, calcium of 25 milligrams per liter. And you see 50 milligrams per liter breaks to at whatever 500 bed volume. The 25 milligrams per liter, you can see 1200. So then you go back and do mass balance. And in this case, when we do the mass balance, we found that the calcium calcium removal capacity is 3.75 milliequivalent per gram, regardless of influent calcium concentration. Which is good to know because if calcium concentration plays a role, then our calculations need to be revised. So this is straightforward classical ion exchange confirmation. Right. So then, how about regeneration? Well, we carried it out at an EBCD of 6 minutes, and this is carbon dioxide sparks no melt at 100 psi. And I would like to show you the difference between resin and the fiber. If you take the resin, then the resin, of course, the acid that you're forming with carbon dioxide, that is so big that the resin doesn't really want to let go of the calcium. That's why you see the resin leading calcium, but it kind of goes on and on. It doesn't end even after 300 bed volume. Whereas the fiber, as you can see, this one, which is cycle 1, much better regeneration. Within 125 bed volumes, we were able to get out more than 95% of the calcium. Now, whenever we present this result, people say 125 bed volumes is very high. And the answer is yes, it is high, but keep in mind this is carbon dioxide, this is flue gas, it is the waste material. So for the waste material, we cannot put the same kind of strictness as we would with a mineral acid, for example. Right?
What is the concentration of to the column?
Concentration of CO2?
CO2.
This is flue gas. I mean, of course, this column, experimental column was with the carbon dioxide cylinder. This was, if I remember correctly, 19%. But that 90% is for flue gas. I think we use a little higher than that.
Regeneration.
Pardon me? For regeneration, yes.
For regeneration purpose,
Yes.
saturation value will be.
Yes, this is much below saturation. Yeah.
Concentration, I think, doesn't matter. If it changes the pH below the pK of this carboxylic group, I think it will be regenerated.
Yes, but what concentration will bring you that pH? That is what you want to know, right?
And sir, another thing is that in your regeneration term,
Yes.
Sir, you get your regeneration within 150 bed volumes for your nanofibers because due to faster kinetics.
Yes, absolutely.
Because it has taken so functional group is available only in your surface.
Yes. In fact, that's exactly what I was trying to show you. This. So, if you look at the fiber surface, then the carboxylate groups are pretty much exposed, right? And so they are so much easier to reach. And if you are looking at the resin, then how would you reach with your carbon dioxide in this case? How would you reach? So what happens is you form a shell, and after that, as you can see, it's almost impossible for carbon dioxide or H plus to penetrate because H plus concentration is so low. This is pH of about 4, 4.2, 4.3, that. So this is what I was just trying to say, that the difference in diameter between the fiber and the resin, and the fact that in the fiber, all the functional groups are available on the surface, whereas with the resin, the functional groups are located throughout the cross-section. These are the primary reasons that carbon dioxide works very well for fiber, but will not work for the resin bead. And so when you look at, for example, this case, copper, for example, right? Copper, if you see, it can only penetrate so much. So this is 19 psi, that is 100 psi. So this is, Dr. Kumar was asking this question, what was the partial, what was the pressure? So when we do pure carbon dioxide, we then have a pressure of 100 psi, and of course 19% of that. But you see that there isn't much of a difference between 19 and 100. So then I'll just skip this. This is basically the same resin now used to remove arsenic, the same fiber to remove arsenic. And again, you get what is known as the F. F means fraction of the counter ion. So I'll just skip this. Then comes perhaps the more interesting application that we had in mind, and that is in an anaerobic process, how can we use the fiber? And now you might say, well, why is there a need for a fiber? Anaerobic process is a microbially mediated process. What is the fiber doing here? And the answer is that if you look at traditional anaerobic process, of course, we saw on day one that you get methane, which has very good, it's a fuel, it has very good heating value. It produces very little sludge. It doesn't really need any energy. It generates energy. But the thing to keep in mind is that anaerobic processes have been susceptible to failure for many years. They're not at all very stable. What do I mean by that? Well, what I mean by that is if you have a situation where you are bringing in the raw material, the feed, the carbonaceous material, well, as you know, this process is simplified as a two-step process. So in step one, you get aliphatic acids, and then the methanogens kick in, and they take these aliphatic acids and they convert it into CH4 and CO2. Very straightforward. Now, what can happen and what does happen is that if you have, let's say, some toxics coming into your feed, then we know that the acetogens are very hardy, very robust. They don't really get compromised. Their performance does not get compromised a lot. So we have seen situations where everything was working fine, but then because of introduction of certain compounds in your feed, the acetogens don't seem to mind. They keep working and they produce these aliphatic acids. But the methanogens, very sensitive to pH, they are very sensitive to other toxic ions, for example, like ammonium. So what does happen many a time is that there is something coming into the feed. The acetogens don't seem to mind, but the methanogens, they stop. Now what will happen? If you can see, the acetogens, they are doing their job. The methanogens are not doing their job. What will happen is that you will keep forming more and more aliphatic acids. As you form more aliphatic acids, the pH goes down. As the pH goes down, the methanogens stop even more. And slowly the process becomes a failure. It's a negative feedback loop, as we say. So the idea that we had in mind is, can an ion exchange fiber be put in an anaerobic digester so that if you have toxic cations coming into the feed, that fiber can take care of the toxic cations such that this process will go smooth. That was the idea. Okay, so this is what we have in mind. So the wastewater goes into acetogenesis, forms acetic acid, goes into methanogenesis, forms methane and carbon dioxide. Now, if there is toxic metal in the feed, it will affect this process. if I put in this ion exchange fiber, then the fiber would be able to take up the toxic metal. And so you see it has, let's say it's originally in calcium form. It will then take up the metal, it will release calcium. Calcium is not a problem in the digester. And the second equation is that now, when this is now loaded with the heavy metal, then because there is so much calcium outside, this will take place by itself. So what will happen is that you bring in a toxic ion in the feed, let's say. It will take up this, but because of equilibrium, it will not be able to hold it for a very long time. It will bleed this metal slowly. And that, I think, is very good in our case because this is what we call regeneration-less system. So we are not taking out the fiber because, as you know, in an anaerobic digester, you have to maintain this redox and this reducing environment so much. You can't really expect to take out the fiber off. But in this case, you don't have to because a slug comes in, taken up, and then this toxic metal is slowly released by the membrane, and hopefully this will go on until the next slug comes. Okay, so that's the idea. And how does it show up in terms of experimental results? This is reactor 1, which does not have any fiber. Reactor 2 has 5 grams, reactor 3 has twice that amount. The 1 liter reactor, we are feeding glucose. This is a lab reactor. So we are feeding glucose at an 18-day HRT. And we introduce at this stage toxic metal, copper. How much? At 500 milligrams per liter. And as you see, reactor 1 pretty much is not able to handle this. And this is very logical. It's nothing really surprising. Reactor 2, well, it does get affected in the sense that the pH starts to drop, but it's still taking up this toxic copper, and what happens is the pH continues to drop, but after a while it starts to pick up again. What does it mean? It means that this reactor has now stabilized. Now the question is, how steep is this drop? And if this drop goes to, let's say, a pH of 4, then of course, no way the reactor can survive. So at its worst, what is the pH? So here you see the pH was 6.8. At its worst, the pH was 6.4. So not a very major, this is not an upset causing situation. But if you put in more material, then it is able to stabilize itself much faster, because this one happens at 80 days, this one happens at 60, whatever, 65 days. So the idea seems to be working. And the other part is, of course, the pH drop is also much less. Now, how about the performance of any digester? Pretty much you measure in terms of methane generation. So methane generation of reactor 1, as you can see, if the pH drops so low, the methanogens stop working, the methane generation would cease. That is what you see. Whereas reactor 2, the methane generation did drop, but after a while, again, it started to pick up. And reactor 3, it did drop, but much lower drop, and it was able to stabilize itself much faster. So the point is that this kind of an approach where we are putting in a weak acid cation exchange fiber, it can absorb some of these shock loadings of toxic metals. And of course, the copper concentration, if you do not have any IXF, of course, the copper concentration it will go straight through in a way. Whereas if you do have the fiber, your copper concentration coming out would be much less. Okay, so what are the conclusions? We were able to create a platform for strong acid cation exchange, weak acid cation exchange, and weak base anion exchange fibers using electrospinning nanofibers. Or nowadays we don't use the word nanofiber, we use submicron because reviewers they don't like. What has happened in nanofiber research is that if you want to publish in these journals, they believe that anything less than 100 nanometers you can call a nanofiber. Anything more than 100 meters, you should call it a submicron fiber, less than 1 micron. You shouldn't call it a nanofiber. Okay, so submicron fiber. Characterization, polystyrene plus polyisoprene, hydrolysis, mathematical model, new application scenarios, and preliminary cyclic tests. This is the question that was asked during the break. Well, keep in mind this fiber does not have any cross-linker. This is pure fiber in a way. And if it does not have any cross-linker, can it absorb these osmotic shocks? And the answer is yes. I mean, the kind of solutions that we are dealing with, their osmotic potential pressure is kind of much lower than, let's say, in an RO or that kind of scenario. So in this situation, it's able to absorb that without much of a problem. Okay. So now, questions. Questions. Okay, so now we will do a short tutorial, and this will be based on the material that we actually covered yesterday, in the sense that we will be looking at cation exchange resin or chelating resin, weak acid cation exchange resin that is trying to remove copper. So we will look at two situations. So please take out your calculators. So we will look at two. So we are trying to remove copper, and copper is present at 10 milligrams per liter. And besides this copper, we also have sodium. And calcium. And the pH is 6.6. So we want to remove, of course, the copper, right? So this is an industrial phase water. And we have two situations. One is strong acid cation exchange. That means it has sulfonic acid functionality. And in this case, alpha, copper, calcium is less than 1, 0.9. And alpha, calcium, sodium is and the other one is a chelating exchanger. Weak acid chelating exchanger. aminodiacylate functional group. And here alpha, copper, calcium, 75. So you see, it's a much more selective resin. Why are we doing this example? Just to show you that the choice of the resin becomes very critical. And alpha, calcium, sodium is 8. Both resins have capacity the same, which is 1.2 equivalents per liter. And so what is it that we have to do? We have to find the YC. Find YCU for both resins. Of course, that will be. And then, so this is A, B would be how many bed volumes? How many bed volumes can we treat with 1 liter of each? Okay. So, we have to look at the aqueous phase and see the X of each. So, copper is 10 milligrams per liter. Calcium is 100 milligrams per liter. And sodium is 250. And so we have to find equivalent concentration. Equivalent concentration milliequivalents per liter. So copper, its ionic weight is 63.54 because it is Cu2 plus. Its equivalent weight is half of that. So half of 63.54 is what? 31.77. So if you divide 10 by 31.77, what do you get? 63.54 divided by 2. 0.1. And calcium, its ionic weight is 40 and 20, so equivalent weight is 20. So this is 5. 100 divided by 20 is 5. And sodium is 23, and this is monovalent, so 23 is equal to
10.86.
And so what would be the xi? So 0.31 divided by all these three. So this is how much is the sigma? 10.86 plus 5 plus 0.31.
16.17.
So 0.31 divided by 16.17 is
0.09.
2.02. And for calcium,
0.3092.
1. And this is 0.67, right?
0.67.
And so this is a good check that this has to be equal to 1 by definition, right? So I have to generate some space, so I'm going to erase all this. So keep in mind the governing formula is that yi equals xi over xi plus summation. What is the summation when j is not equal to y? Alpha ji. So which means that CA equals XCA divided by XCA plus alpha CU CA XCU plus alpha NA CA. This equals to XCA is 0.31 divided by 0.31 plus alpha CUCA. Alpha CUCA was 0.9 for the first one. 0.9 multiplied by 0.02 plus alpha NaCA. How much was it given? Alpha NaCA was 1 over 4, right? 1 over 4 multiplied by 0.67. How much is this?
.625.
0.62. So this is the first resin, strong acid. And similarly, we can find YCU. YCU is XCU. This is XCU is 0.02 divided by 0.02 plus alpha CA by CU is how much?
1 by 0.9.
1 divided by 0.9 multiplied by 0.31 plus alpha NaCO is
0.25. Sorry, this is not.
that again?
Sir, we have 3 species,
Yes.
so we need 3 alpha.
No.
So if you multiply
I
the
think this is not correct. This is not NaCO. Alpha J versus I. In our case, I is copper and J is sodium. Right? So sodium over copper. Say that again? No, it will not be 1 by 0.9. You are correct.
A by C.
So we are still doing strong acid.
0.9.
So alpha Ca over Na was 4. Let me erase this. One can get the third one from these two. That's what I was trying to.
If you multiply these two.
Yes, exactly. So let me just. So we were given that alpha Ca Na is 4, right? Which means YCA over XCA divided by YNA over XNA equal to 4. And we are also given that alpha CuCa is 0.9, which means YCu over XCu divided by YCA over XCA is 0.9. So now you see, if I take YC over XCA is 4 times YNA over XNA. And if I put that here, I will get for Cu over Na. Right? Is it clear what I was saying? What I was saying is, so from here, YCA over XCA is 4 times YNA over XNA, right? Now I put that in here. YCu over XCu divided by 4 times YNA over XNA would be equal to 0.9. Therefore, YCu over XCu divided by YNA over XNA would be how much? It will be 0.9 times 4, right? 3.6. And this is nothing but alpha Cu over Na, right? Agree? And so alpha Na over Cu would be inverse of it. And so alpha Na over Cu is 1 over 3.6 times XNA was, I now have erased it, so XNA was it 0.67. XNA was it 0.67? So how much does it come to now? 0.0. Very good. So let me erase all this because I need all this space. Now I have to leave in a few minutes. So I will give you the corresponding numbers for the second exchanger. We will not have the time to do all the calculations here itself. So YCA is 0.625, YCu is 0.036, and so YNA would be 1 minus these two, right? And that comes out to 0.338. Now if I look at the chelating exchanger and I do the same calculations, what I get is, and as I said, I would have loved to do this with you, but because of the other commitment, I cannot. So these would be the values. Please, when you go home, check them. If you get different, let me know. We now see that YCu has increased manifold. Okay, so 0.036, now it has become 0.8. So the point of this example is that when you have to remove a toxic heavy metal cation, you need a chelating exchanger because the strong acid cation exchanger would not be selected. Okay. So now just the other part is your Q is, we said, is 1.2, is it? Equivalents per liter. And YCU for the first one is 0.036. Is it? Zero point zero three six. So what is the capacity that you get for copper? Yeah.
1.2 into 0.036. 0.043.
0.0.
432.
Equivalents per liter. And we have how much? We have 1 liter, is it? Okay. So in the water, how much copper do we have? 0.32 milliequivalents per liter, right? So 0.0432 times 1000 milliequivalents per liter divided by 0.32.
The 1 liter multiplied by concentration of copper divided by Q.
Yeah.
We will get the volume of water.
We will get the number of wet volumes of water treated. So this is multiplied by 1 liter actually. So liter cancels. Milliequivalent. How much is this? How much volume are we treating? This is 43 divided by 0.32. 135 bed volumes. So you can treat 135 bed volumes of this water, whereas for this, you do the same calculations. You will see
0.8 multiplied by 1000.
0.8 times 1.2 is 96, right? 0.96. 0.96 times 1000 divided by 0.32. How much is it?
3,000.
3. So you see, I mean, if you use a chelating exchanger, you can treat 3000 bed volumes of this water, whereas if you use the strong acid cation exchanger, you can treat only 135 bed volumes. Okay, so we'll stop here. Questions?
Sir, for regeneration purpose, during time, I will regenerate.
Which one?
This one, I know the first one,
Hmm.
but for the second one, the process is same.
The second one is actually a two-step process. In the first step, we regenerate with an acid, and then in the second stage, we then pass sodium chloride to put it back in sodium, the exchanger.
And sir, concentration will have about 4% for any cell.
Concentration, say that again?
If we set the regenerate, so we set the concentration about 3%.
3% of what?
Yes.
For a weak acid, cation, exchange resin, NaCl, 3% may not be needed. I think half of it should be good enough. 1.5%. Yes, strong acid you have to kind of drive out the calcium. Here it's just you are raising the pH, so the H plus comes out much easily.
Then I'll send 1.5% of NaCl solution.
That should be good enough. And of course, you have to raise the pH.
And sir, how many weight volumes are possible?
with immunodiacetate, anything between 15 to 20 bed volumes is good. Roughly, of course, yeah, everything is.
Answer, how many cycles we can use such kind of medicine?
Oh, we can use very safely at least 600, 700 times. In fact, even beyond.
Is there any fouling finally covered such kind of medicine?
If your solution is pure, not really. Okay, so we will disperse for lunch, and then, as I said, I will not be able to join you in the afternoon because I am now leaving for Assam University. I have a seminar to give there at 2 o'clock. So I will see you again tomorrow. Thank you.